Now let's move to the second part, which is this part. We now want to show theta to T2x. We have a Markov chain. So for first, we note that we consider this probability. So probability that x is equal to a particular vector realization. So we have x1 equal to 0, x2 is equal to 1, all the way up to xn. A particular realization given data is equal to c. Then this particular realization, the probability can be given this way, because c is the probability that xi is equal to 1. So we have this one for random variable x1. So random variable x1 is equal to 1 with the probability of c. So when x1 is equal to 1, I need to have c as a probability. So in order to make sure that that is the case, let's consider that x1 is equal to 1. Then this later part, x1 is equal to 1 is the 0th power. So 1 minus t taken to the 0th power is 1. So that is correct. So probability that x1 is equal to 1 is a c. But in this, for example, of this particular case, we can also have the probability of 1 minus c. So probability that x1 is equal to 0 should be 1 minus c. Let's make sure that it is the case. So when x1 is equal to 0, then c to the 0th power is 1. C to the 0th power is 1. And when x1 is equal to 0, so this exponent is 1. So that is 1 minus c. So, okay. So the probability that x1 is equal to 0 is 1 minus c. So this general expression works for any x1, x2, and so on. So any value of x1, it works. So let me now make it general. So after I have done that, I can make it general. So, oh, sorry. So no matter what each dummy variable takes, right, this expression is correct. So once I have this general expression, then I can collect these product terms. So that is nothing but c to the summation of all xi's. And then when I collect for terms 1 minus c, there is nothing but 1 minus c taken to the power of n minus sum of xi's. Okay, so having this general expression obtained, we can move on to the next one. So second, note that probability of x, which is a vector, that I have a realization of t ones in the vectors, and then data is equal to c. In such a case, I have c to the power of t, basically, because there are t ones in these summations. So it is c to the taken to the power of t. And then the later term is n minus t. Okay, 1 minus t, c taken to the power of n minus t. So that's the case when the realization of x has t number of ones. So that is the expression in such a case. Now, third, we want to note this one. Now we want to consider conditioning. T given small t included. Okay, what is this probability? So basically this one, by conditional probability, it can be written as joint divided by the marginal. So data is given C, both terms, and then T is the condition, so I have to have this one. Okay, so that's the result obtained from applying the definition of conditional probability, the first line, and then I kept the numerator as it is, and then applying the total probability theorem, I obtained this one. Okay, so I consider every possible vector x. Okay, and then once I have done this and making use of previous results, the numerator is c to the power of t, 1 minus c, and minus t. Okay, and then the denominator, the jointly with the this joint event is that out of n positions, there are t positions where you have ones. So that is n choose t such possible combinations. And for each combination, the probability of having t ones and the rest of them or zeros is this probability, as we have seen in previous case. I mean, as we have seen here, right? So that's this probability. So that's the sum of all possibilities. And as you have done that, this is the case when this there are this many ones. So t1s. If there are t1s in this case, this is the case. When there are no, when the number of ones in here is not equal to t, the probability is equal to 0, because this is the given condition. So this holds if the sum of ones in n trials is equal to t. Otherwise, it is 0. And as you have noticed, the numerator and the denominator has the common term, so we can cancel this out, and we have left with 1 over n choose t. So there are, I mean, this term, we notice that there is no involvement of c. So c disappeared. So the dependence on c has disappeared. So as you can see from this, we can have this probability equal to probability of x given t only. So given t, we have no dependence on data. So that's it. So, but in order to make sure that we can consider fully, so we that's the fourth item. So we consider in this case probability of x given t equal to t. We already know that this will result in the same, but we can do some practice. So what matters the case where the sum satisfies this case, as we have seen here, if the sum is not equal to t, the term is equal to 0, so we only consider those cases in order to simplify the matter. So here the probability that the x is equal to a vector whose number of ones is equal to t. Okay, so there are t ones in this vector. So we consider this, and that one, by the total probability theorem, we have this. So nothing changed. All I have is joint probability, taking data into consideration, and then given condition stays the same. And then using joint probability, using conditional probability, I condition on data, and then I have this term appears. So since I have conditioned here, I have to multiply with this probability. And then once I have this term, and then utilizing previous result, that this probability is 1 over n choose t. So this is a constant, so I move this one outside, and then have the integration move inside. Then basically this probability is equal to 1, and then what I have left is 1 over n choose t. So basically that's it. So I have proved that there is a Markov chain relation from theta to t to x. Okay, so that's the end of the proof. So I have given you an example that t given this way is sufficient statistic.